That was close. Okay. Yeah, so the null space, if we're given an m by n matrix A, the null space of A is going to consist of all of the solutions of the equation AX is equal to 0. So the column space was the space of all linear combinations of the columns, which is equivalent to saying it was the solutions to the equation AX is equal to B. The null space is the set of solutions where AX is equal to 0. And so just like the column space, the null space of A is going to be a subspace of Rn. So if we wanted to show that it was a subspace of Rn, we would have to show that it's closed under addition, and we would have to show it's closed under scalar multiplication. So to show that it's closed under addition, you would take two elements, x and y, in the null space. If they're in the null space, that means a times x is equal to 0, and then a times y is equal to 0. And then if you were to add them together, you would end up getting the following equation. So a times x plus y ends up being equal to 0 if you just distributed the a. So you had a times x plus a times y. It would just be 0 plus 0. So that tells you that it's closed under scalar, or it's closed under addition. And then it's closed under scalar multiplication, because if you have that ax is equal to 0, then if you multiplied by some scalar multiple c, you can bring the c in front. Like you can pull, like it's just a scalar, so you can move it outside of the parentheses and in front of the a, in which case you'll just have c times ax, which would give you 0 again. So it's closed under addition, it's closed under scalar multiplication, so the null space is going to be a subspace. Okay, so this is just recalling two definitions that we've seen in the past. So we saw before, this is how we defined whether or not we had independent or dependent columns. So if we have that AX is equal to 0, this tells us we're going to have infinitely many solutions when the columns of A are dependent. So if we have dependent columns, we have infinitely many solutions. And then we saw that if AX is equal to 0 has a trivial solution, then the columns of A are going to be independent to one another. And so this is kind of technical language. We'll be able to relate this idea of column dependence and independence based off of the pivots of a matrix, and then what are called free columns of a matrix. So once we work through an example, it'll be a lot more clear about like when the columns are going to be dependent and where they're going to be independent, just from doing row operations. Okay, so to understand the null space, it's a good idea to work through an example. So we're going to consider the following matrix. This is going to be a 3x4 matrix. And then we're interested in solutions. If we're interested in the null space, we're interested in solutions of the following equation. So we're interested in multiplying A by some 4x1 vector. And then we would end up getting a 3x1 vector. And we want to set it equal to 0, 0, 0, right? If we're interested in the null space, right? This is the same thing as it saying like we're interested in equations of the following form, right? Where this is our x. And so if we want to understand the null space, you just do what we've always been doing in this class so far. You just take your matrix and then you use row operations to reduce it to upper triangular form. And then you can use back substitution to understand what the null space is going to end up looking like. And so what's particularly nice about finding the null space is that we're going to be solving an augmented matrix where the final column is just going to be all zeros. So row operations isn't going to have any effect on it, because you'll just be doing like, if you did like row 1 plus row 2, it's just 0 plus 0. If you did like row 3 minus row 2, it's be 0 minus 0. So you really don't have to keep track of the augmented portion of the matrix. You can just, well, I have it on the next slide. Right? Like if we want to understand the null space, it's really just saying like, we're considering, how do I want to do this? I should have adjusted this slide, but like really we're concerned with the following augmented matrix. But when you perform the various row operations, there's no effect on the final column, right? So you don't even have to write it down, really. Like it's just superfluous. So if you go through and perform the various row operations, for instance, you'd do, like if you wanted to get rid of this 2, you'd do -2 times row 1 plus row 2. you'll get the following row. If you did row 1 plus row 3, you'll get the third row right here. What matters is what you ultimately get as your upper triangular form. So if you're writing notes and it's kind of like writing, it's a lot of writing, I'd recommend just starting off by writing the first matrix and then writing what the upper triangular form is at the end. That way you're not like writing so much. And then I guess if you're want practice, you can like go through the individual steps later on and verify you actually end up getting this upper triangular form. And so when we reduce to this upper triangular form, what we want to observe are the pivots of our matrix. And so the pivots, these are just like for every single row, the pivot is going to be the first non-zero entry of your row, right? It's something that we've seen before and discussed before. So the pivots of this matrix is going to be the 1 in the first row, the -1 in the second row, and then the 4 in the third row. So we have 3 pivots, and we should be thinking in terms of columns actually. So there's like a way of thinking of things in terms of rows and in terms of columns. So we have 4 total columns, and we have 3 pivots. And so this final column here, let's use a different color. It's kind of the column that's left out, right? It's the only column that doesn't contain a pivot. And so we're going to call this a free column. And so in understanding the null space, it has a high score, like it corresponds to having an understanding of the free column. So whenever you think of free columns, it's going to give you the size of your null space. So we have 1 free column. So this is going to end up telling us the dimension of our null space. I'll talk more in detail about this later on. Well, I should say free column, not free columns. I'll talk more about this later on, but the number of free columns you have corresponds to the dimension of the null space, just as the number of pivots you have corresponds to the dimension of the column space. So you can kind of already see, and this is something we'll talk about in more detail later, that the sum of the dimension of the column space plus the dimension of the null space is going to be equal to the number of columns that you have. We have 4 columns, we have 3 pivots, and then 1 free column. Like 3 plus 1 is equal to 4. We have 4 columns. So I'll write this down more rigorously later on, but just to develop like an understanding in the beginning. So we have that A has 3 pivot columns, and then we have 1 free column. And so if you think back to how we originally were setting up these matrices, they relate to systems of linear equations. So each of these columns correspond to a variable. The first column is x, the second column is y, the third column is z, and the fourth column corresponds to the variable w. We have 4 columns, so we have 4 variables. And so this gives us a way, if we set this equal to 0, right? Because I'm like talking a lot about this, but it's important, right? We are really considering the following augmented matrix. So we're setting each of these rows equal to 0, right? And so if we set these equal to 0 and then we solve using back substitution, we'll get the following result. So we have that 4z is equal to 0. That's written right here. So this will imply that z is going to be equal to 0. The second row tells us that we have -y plus 3z minus 4w is equal to 0. So if you work with this equation, we know z is equal to 0. So you ultimately get that y is equal to minus 4w. And then the first row tells us that we have x plus 2y minus z plus 2w is equal to 0. And so if you plug in for z and y, you can express x entirely in terms of w. So if x is equal to 6w. And so if we want a description of the null space, right, the set of solutions to ax is equal to 0, all we have to do now is, like, this following vector gives us all the information that we need, right? So if we take a generic vector, say it's like x, y, z, w, using this information that we obtained from back substitution, we can rewrite this in the following way. So we have that x was equal to 6w, so you can say that this is equal to 6w. Y was equal to minus 4W. Z was equal to 0. And then we have W is equal to W. So we can write the solutions to AX is equal to 0 in the following way. Like the answers, like the solutions only depend on W. And you can think of like factoring out the W. And so the null space is really just going to be the scalar multiples of the following vector. So if you take out the W, you just have 6, minus 4, 0, 1. And so this is going to be your null space. Like this is the set of all solutions of the equation AX is equal to 0. And it's parameterized by the single variable W. So this is going to be like the null space. So the null space of A, this is equal to the set of all scalar multiples of 6, minus 4, 0, 1, where we have that W as a real number. And so what we're seeing is if we have a non-trivial null space, we're going to end up having infinitely many solutions, right? Because we have like a one-dimensional null space. So the set of solutions is parameterized, or like for every W you have on the real number line, you have a corresponding solution. So we have infinitely many solutions to the system of linear equations. And we'll go through a lot more examples today and on Friday as well. But any questions so far about finding the null space or how we obtain this quantity here? Okay. Yeah, so there's going to be more complicated examples where you have like multi-dimensional null spaces, but they all kind of play out the same way. You have to understand your pivot columns and your free columns. The number of free columns tells you the dimension of your null space. And so the book introduces this terminology, which I'm not a huge fan of. It's not something I really ever make use of, but it describes something as being a special solution. So they say a special solution is obtained by setting one free variable equal to 1, while choosing 0 for any remaining free variables. So I should say like W is the free variable in our previous example, right? We had W was the free column, like the free column corresponded to W. So we have W is the free variable in the previous example, just to make sure that the notation is clear. And so if we want to obtain the special solution, what it's suggesting is we just plug in W is equal to 1. If you plug in W is equal to 1, you just get this vector right here, right? So like the conclusion they're trying to get to is that the null space is the set of linear combinations of the special vectors or the special solutions that you obtain. But I think it's kind of easy, like writing it out in the way that I did before, it's kind of easy to see like what the special solution is going to end up being, right? You just take out the W, so you have like W times this thing. But yeah, if you have, like if you wanted to, you can set W equal to 1, you can see you get the same thing. So yeah, in this case, the only special solution is the following. It's exactly what we saw before. And so as we saw in the like I already wrote this out already, but the null space of A consists of all multiples of the vector 6, minus 4, 0, 1. It's exactly what I had written up on the previous slide. Okay, so in general, there should be only one special solution for each free column in the set of linear combinations of the special solutions end up filling up all of the null space of A. So we'll see that in examples. Okay, so this is another really important idea. So far in this class, aside from finding inverse matrices when we're doing row reduction, we've always just stopped when we got to upper triangular form. But you can go a little bit further if you're, in finding like special solutions in this like null space, it's usually beneficial to go further than just going into upper triangular form. Your goal is you want to avoid doing back substitution. So if you wanted to avoid doing back substitution as much as possible, you can reduce your matrix into what's called reduced row echelon form. So if you want to reduce your matrix into what's called upper or reduced row echelon form, you're going to continue going on from the upper triangular form. And for every number above a pivot, you want to end up making it so it's going to end up being equal to 0. And then for every single pivot, we want it to be equal to 1 instead of being like 4 or minus 1. So if we took the previous example, this is where we stopped before. This was the upper triangular form. You can go further by eliminating this 2 that's above this pivot in the second row. So if you did 2 times row 2 and you added it to row 1, that would get rid of this 2. So you would end up getting a 0 here. After doing that, you can make it so instead of having a -1 as your pivot, you can multiply the second row by -1 to make it so the pivot is going to be 1. And then similarly for the third row, instead of having a 1 or instead of having a 4 as your pivot, you can multiply by 1/4 to get a 1 as your pivot. And then we can get rid of this -3 above this one by multiplying 3 times row 3 and then adding it to row 2. Right? And so we end up getting a matrix. If we keep on going and we reduce our matrix to this new form, like this reduced row echelon form, we end up getting the following matrix, right? Where the 3 by 3, or at least this first 3 by 3 is the identity matrix. It's not always going to play out this nicely, but we see we have like the identity matrix here. And then in the fourth column, we have the -6, 4, 0. So you can kind of read off what the special solution is going to end up being just by putting it into reduced row echelon form, right? Like the special solution, I don't know if people can see when I zoom out this much, but the special solution was 6 -4, 0, 1. And so you can see like the 6 here corresponds to adding 6 over to the right-hand side. This -4 corresponds to subtracting 4 over to the right-hand side. And then the 0 corresponds to this 0 right here. So it's more easy to see what the null space is going to end up looking like without having to do any back substitution whatsoever by going into this reduced row echelon form. So this is kind of the standard for row reduction. Like you usually don't simply just reduce to upper triangular form. Like from this point onwards, usually you want to be reducing to this reduced row echelon form. So the matrix R in the previous example, or not really the previous example, but this matrix R obtained from, how do I want to word this? So the matrix R is the reduced row echelon form of the original matrix A that we had. So this is our R in reduced row echelon form. And so what really matters about this, and in terms of like column space and null space, is that when doing this reduced row echelon form or row reduced echelon form, the pivot columns and the free columns remain unchanged. So by doing this more sophisticated row reduction, it's not going to change the null space or the column space, is what this is saying. The pivot columns don't change, the free columns don't change either. You're still going to have the same number. So it doesn't affect the size of your column space or null space. And then, as I said before, it's easy to determine the one special solution that ended up spanning the null space. Okay, so this goes into, like the next slide goes into what I was saying before. Oh, I should probably leave the definition so if people want to write that down. So this next slide just goes into what I've been saying already. So the example that we saw before illustrates an important fact about the null space of an m by n matrix. So if we only have m rows, I don't like that's when I was learning this stuff, it was reduced row echelon, and they're calling it row reduced echelon. It's messing me up so much. I'm just going to call it reduced row echelon form. I think that's how 99% of the population says it. So the reduced row echelon form can have at most m pivots, right? If you only have m rows, you can't have m plus 1 pivots. It wouldn't make any sense. You can only have at most 1 per row. So if we end up having that there are more columns than there are rows, there's going to be at least 1 free column, right? So if we have more columns than rows, it means we're going to have infinitely many solutions. Well, it means we either have no solutions or infinitely many solutions, right? You should be associating free columns to having infinitely many solutions. And so each free column that we have adds 1 to the dimension of the null space. So if we have 1 free column, the null space is going to consist of multiples of 1 special solution. This is what we saw before. It was the null space was W times 6 minus 4, 0, 1. If we had 2 free columns, the null space consists of linear combinations of 2 vectors. That's 2 typos. So you'll have like a linear combination of like CV plus DW for some vectors V and W that you need to determine. And then if you have K free columns, the null space is going to consist of linear combinations of K vectors. So it's going to be K dimensional. And we haven't really talked about dimension of a vector space yet, but I think it's something we talk about in either section 3.4 or 3.5. But it depends, like, you should be thinking of dimension in terms of how many vectors it's like are required to, like in the linear, like how many vectors are required to have like a linear combination that can represent any other vector in the space. We'll define it more rigorously later on. Okay, so this is important to know. Like the number of free columns ends up giving you the dimension of your null space is the main takeaway for this part. And so we've been talking about the dimension of a null space. The next definition, this idea of rank, is going to be talking about the dimension of the column space. So this is another really important definition that's going to show up throughout this class. So if we have an M by N matrix, the rank of A is going to be the number of pivots in the row reduced echelon form R of our matrix. So in a sense, the rank is going to measure the true size of our matrix in terms of the column space. In fact, like the two ideas are exactly the same as one another. So the rank of your matrix is exactly the same as the dimension of the column space. So just by definition, on Monday, we said the column space was determined by which columns have pivots in them, right? And we went through an example. Well, let me pull up the example. You probably don't like have this memorized just from seeing it once. But on Monday's class, we worked through this example. We took a matrix and we ended up reducing it into the following form. So we had two pivots. I'm going to actually pull up the solutions to this. So we ended up having like the column space for this example. We were able to reduce it to the following form. So we had these two pivots in the first two columns. And so this told us that the column space was going to be the space of linear combinations of the first column of our matrix and the second column of our matrix. Right, so we had a two-dimensional column space because we needed two vectors in our linear combination. And we'd also see like the rank of this matrix would be equal to 2 because we have two pivots. So the dimension of the column space is exactly the same as the rank by definition. They both depend on the number of pivots that you have after reducing your matrix. Okay. Yeah, so I have this written. So in particular, the rank R of a matrix A corresponds to the dimension of its column space. Okay, so now we're going to work through a couple of examples to conclude this section. Just two more examples. So we're given A. It's going to be a 4x3 matrix. And so it wants us to do a couple of things with this matrix. It wants us to describe the null space of A in terms of special solutions. And it wants us to actually determine what the null space is going to be. And then it also wants you to find the rank of A and the dimension of the column space of A. So just like any other process or like anything we want to know about a matrix, we always just perform row operations and row elimination. So we start off with our original matrix, 1, 2, 1, 3, 8, -1, 2, 4, 2, 6, 10, 5. And so if you wanted to reduce this matrix, usually the first thing you want to do is just remove anything that's beneath the 1 we have in the 1, 1 entry. So we'll keep the first row the exact same. We'll do -3 of row 1, or yeah, -3 times row 1 plus row 2. That'll give us 0, 2, and then -4. If we wanted to get rid of this 2 in the third row, we'll do -2 times row 1 plus row 3. That's going to give you 0, 0, 0. And then to get rid of the 6 in this final row, you'll do -6 times row 1 plus row 4. That'll give you 0, -2, and then -1. And so you see that we have a row of zeros that we obtain. And so usually if you have a row of zeros, this doesn't really matter, but I always just put it at the bottom. So I'm just going to take this original, like this matrix we have here. All I'm going to do is switch row 3 with row 4. Just to make life a little bit nicer. And then next thing we want to do is we want to get rid of this -2 that we have in the third row. So you can add row 2 to row 3. If you were to do that, I'm just going to copy and paste. If you were to do that, the only thing that would change would be the third row. So you would have 2 plus -2 would give you 0. And then you would have -4 plus -1 would give you -5. And so from this point, what you can do, so we have it in upper triangular form, which is nice. And we can actually determine what the null space is going to be already. Does anyone see what the null space is going to be from looking at this matrix? I guess like another question would be, oh, okay, go ahead.
There is no null space.
Yeah, pretty much. Like it's just going to be the 0 vector. Without even going any further, actually we could stop right here. I am going to put in reduced row echelon form, but everything we need to know is actually already given to us because we have 3 columns, right? Corresponding to 3 variables. And in each of these columns, we have a pivot, right? So every single column has a pivot. So we don't have any free columns. So that tells us that the null space is going to be 0 dimensional. Like it's just going to end up being a point. So we have that the null space, well, I'm going to write it below because I'm going to keep going and put it in reduced row echelon form just to show you what it ends up looking like. But it's worth noting that we can stop here, right? Because we have that the null space. So we have no free columns. So this is going to imply that the null space of A is just equal to the 0 vector. Okay, so this means that the dimension of the null space is going to be 0 dimensional. I think that was the 2 questions that it wanted. So we have a description of the null space. It's just the 0 vector. We know what the dimension ends up being equal to. The second part is it wanted us to find the rank of A and the dimension of the column space of A. Again, the rank of A and the dimension of the column space are the same thing. And we have that they're determined by the number of pivot columns we have. So we have 3 pivot columns. Implies that the rank is equal to 3. And this is the same thing as saying that the dimension of the column space is going to be 3 as well. Again, you should find that the dimension of the column space, or maybe I'll put things in terms of rank. So the rank plus the dimension of the null space should be equal to the number of columns that you have. So we have the rank is 3, dimension of the null space is 3, you add them up, and you have like the 3 columns. So that's one thing to remember. It's something it's an actual theorem that we'll talk about. I don't know when exactly, but yeah. So that's what the column space. So the column space would just be the span of these 3 columns right here. They're independent to one another. And so if you wanted, we're done with this problem, but just to illustrate what the reduced row echelon form would look like, you can keep on going. You'll keep the first row the exact same. If we wanted reduced row echelon form, we would make it so this first pivot, like the pivot in the second row, would be equal to 1. So you would divide the second row by 2. So you would get 0, 1, -2. And then you'll divide the third row by -5 to get 0, 0, 1. And then once you're in this position, you can just add row, like 2 times row 3 to row 2. The only thing that would change is you'll get rid of this -2. And then if you did row 1 minus row 3, the only thing that would change is you would get rid of this 1. So you can easily get rid of the -2 and the 1 that's above this one right here. And then you can do something similar with this too, right? Well, I'm going to do it just step by step. So this is 1, 2, 0, 0, 1, 0, 0, 0, 1, 0, 0. We just got rid of this -2 and this 1 via this one in the third row. And then you just have to get rid of, like, to get rid of this 2, you'll just do -2 times row 2 plus row 1. And the only thing that would change is the -2 would be eliminated. So you kind of have a copy of the 3x3 identity matrix that make up the first 3 rows of this matrix, right? So reduced row echelon, in an ideal world, like, you want to be able to always reduce it to the identity somewhere, but it doesn't always play out this way, as we'll see in the next example. Okay, any questions about this example we just worked through? Okay, yeah, so the next example is going to be a bit more interesting. So for this example, it wants us to find the reduced row echelon form of A, where A is this 3x4 matrix. And it wants us to find the special solutions of AX is equal to 0. It wants us to find the rank of A, and it wants us to find the dimension of the null space. And so you can already tell that this is going to have, and you have to, like, kind of get in the mindset of, like, what are the solutions going to look like based off of the matrix that we have, now that we know about, like, the null space and column space and all that. From the fact that we have 3 rows and 4 columns, or rather that we have more columns than we do rows, you can already determine that there's going to end up being infinitely many solutions, in the sense that we can have at most 3 pivots. So with there being 4 columns, we have to have at least 1 free column. So you want to have a description of what that free column is going to look like, and you might end up having like 2 or 3 free columns, depending on, like, how these rows relate to one another. Okay, so we'll go through this problem. So this is 1, 2, -1, 3, -2, -4, 1, -3, and then 1, 2, -2, 6. So again, the first thing you want to do is you want to perform some row operations. If you want to reduce this to reduced row echelon form. So to do this, we would add 2 times row 1 to row 2. That would give you 0, 0, -1, 3. And then if you did row 3 minus row 1, you would get 0, 0, -1, 3. And so you can see we have an interesting situation where we have that the second row and the third row end up being equal to one another. And so if we subtracted from row 3, row 2, this third row is just going to end up being a row of zeros. So we end up getting the following. So the first row is going to remain the same at this point in time. The second row is going to be 0, 0, -1, 3. And again, we're subtracting the second row from the third row, and that's just going to end up giving you 0, 0, 0, 0, because the second row is the third row. Be subtracted from itself, we'll just get a row of zeros. So if we want to put this in reduced row echelon form, we want to make it so this -1 is going to be a +1. So you can multiply the second row by -1. I'm just going to copy and paste this. So if you multiply by -1, you're going to end up getting the second row in the following way. And then if we wanted to get rid of, all we can do at this point is just get rid of this -1 that's above this pivot. So to get rid of this -1, you can add row 2 to row 1. And then if you were to do that, you would get the following. So you get the matrix 1, 2, 0, 0, 0, 0, 1, -3, and then 0, 0, 0, 0. And so at this point in time, there isn't really anything else we can do to this matrix. So it looks a little bit wonky, but it's the best we can deal with. Like, we don't really get like the identity as we would hope. And so now at this point in time, like once you have it in reduced row echelon form, you want to start thinking in terms of where the like pivots are. Like what's the column space? So what are the pivots? And then what is the null space going to be? So we have two pivots. We have this pivot in the first row, and then we have this pivot in the second row. And again, the four variables, we have four columns. So we have four variables. We have X, Y, Z, W. And so from this matrix that we have here, we can write X in terms of Y, and we can write Z in terms of W. Right, this matrix tells us, let's see this start blue. So this matrix tells us that we have X plus 2Y is equal to 0. That's what the first row tells us. And then the second row tells us that Z minus 3W is equal to 0. And so this tells us if we subtract both sides, or if we solve for X and Z in terms of these free variables, Y and W, will get the following. So it would have X is equal to minus 2Y, and then we would have that Z is equal to 3W. Okay, and so what this is going to tell us is that if we write out this vector, if we just take a generic vector, say X, Y, Z, W, we can write it in the following way, using the fact that X is equal to minus 2Y, and then Z is equal to 3W. So X is equal to minus 2Y. So the first component can be written as minus 2Y. We have that Y is just equal to Y. We have Z is equal to 3W. And then we have that W is equal to just W. So you can rewrite this in the following way. Like if we're interested in the null space, we're interested in writing out what the null space is going to be as a linear combination of something relating to Y and something relating to W. So you can kind of think of, I was like, how do I want to write this out? So you can write it out in the following way, just as we were doing before. So like think about like what the vector would look like if we factor out a Y. If we factor out a Y, we'd get a minus 2 in the first component. We would have a Y in the second component. And then the second, like this component and this component don't have Y, so it'd be 0, 0. And then if we factor out a W, right, the first component doesn't have a W, the second component doesn't have a W, so it'd be 0, 0. And then the third component is 3W, so it'd have a 3 here. And then the last component has just a 1. Okay. And so this is what the null space is going to look like. The null space is just the collection of all linear combinations of this form right here. So maybe I'll write it out more explicitly. Well, actually, before doing that, like this is the special, like going back, I don't like talking in terms of like special solutions or anything like that, but just to write it out, like this is the special solution you get with Y being equal to 1 and W being equal to 0, right? If you plugged in Y is equal to 1 and W is equal to 0, you'll get minus 2, 1, 0, 0. And then this other vector we have written out as the special solution where we have that Y is equal to 0 and W is equal to 1. Right, so if you plugged in W is equal to 1, Y is equal to 0, you would get the following vector. So that's like where these special solutions come from. I think it's easiest to just write out this vector and then write out what the vector is going to look like in terms of the free variables, because then the special solutions just pop out. Like they don't really require any additional thought, I would say. Okay, so what is this question? What was it asking? So we want to find special solutions. Check. We found the special solutions. We want to find the rank of A. So the rank of A is this equal to the number of pivots of the matrix after doing reduce, like after putting in our matrix into reduced row echelon form, we had 2 pivots. So this is the rank of A is equal to the number of pivots. This was equal to 2. So that's what the rank is going to be. And then I was asking for the dimension of the null space. So the dimension of the null space is just equal to the number of free columns that we have. So this was equal to 2. And again, I'm saying it over and over again, but if you add the rank with a dimension of the null space, you end up getting the number of columns that you have. So like a column, it's either going to be a pivot column or it's going to be a free column. Pivot columns contribute to the column space, free columns contribute to the null space is the main thing that you want to remember. And then to explicitly write out what the null space is going to look like, we have that the null space of A, this is going to be equal to the set of all linear combinations of the following form. So it's exactly what I had written already, but just to write it more formally. So it's a 2-dimensional null space, like the span or linear combinations consist of like these 2 vectors right here. Okay, any questions about this example? Okay, there's one more example. I kind of wanted to go on to 3.3, but we only have a couple minutes left. So let's go through this example and then we'll call it a day. So for this example, we have a 2x4 matrix. So, I mean, we can have at most 2 pivot columns. So we're going to have at least a 2-dimensional null space. You could have a 3-dimensional null space if the first and second rows are linear or are scalar multiples of one another. So just like any other problem where you want to find the null space, you just reduce your matrix. And so the first row is going to stay the exact same. And then you do -2 plus. So if you do -2 times row 1 plus row 2, you get 0, you get a 2, you get a 0, and then you get a -2. And so you can rewrite this. If we want to put this into reduced row echelon form, we can write this as 1, 3, 2, 6. We can divide the second row by 2 to get that this is going to be 0, 1, 0, -1. And then from here, I'm going to move this to the side a little bit like this. So from here, all you can really do is you can get rid of this 3 that's above this pivot we have in the second row. So you can do -3 times row 2 plus row 1. So you 0, 1, 0, 2, and then 9. And so these are going to be the 2 pivot columns. We have a 1 here and a 1 here. So we kind of have a copy of this 2x2 identity matrix. And then the last 2 rows or last 2 columns are going to be free columns. So this is, in terms of variables, we have this is X, Y, Z, and W. And so if we want to determine what the null space is going to be, right, we're really thinking in terms of an augmented matrix where the final column is 0, 0. So we have that X minus 2Z plus 9W is equal to 0. That's what the first row gives us. And then the second row gives us that we have that Y minus W is equal to 0. Or yeah, Y minus, yeah, that's right. So this tells us that we have X is equal to 2Z minus 9W. And then we have that Y is equal to W. And so just as we did before, if you want to determine what the null space is going to be from this point, we can write out a generic vector. So X, Y, Z, W. And then we just want to put everything in terms of these free variables, Z and W. So the free variables, again, are the variables corresponding to the free columns that we have. So we have that X can be written as 2Z minus 9W. we have that y is equal to w, and then z is equal to z, w is equal to w. They're already in terms of free variables. So you can write this, again, thinking in terms of like z times some vector plus w times some vector. So you can think in terms of factoring out a z. So we have a 2z in the x component, so this is going to be 2. We don't have a z component for y. Factor out a z, you just get 1. Then this will be 0. And then this is going to be plus w times minus 9 in the first component, 1 in the second component, 0 in the third component, and then 1 in the final component. And so this gives you a complete description of the null space, right? So the null space, this is going to be equal to the space of all linear combinations of the following form, where we have that z and w are real numbers. So again, we find that two-dimensional null space. And again, saying again a lot, you can determine from the very beginning, based off the number of rows and columns that you have, that the null space was going to be at least two-dimensional. So the only other possibilities are if there's like a three-dimensional null space, which would occur if these two vectors were scalar multiples of one another, or you have a four-dimensional null space in which A is just the zero matrix. But this is the main thing you need to remember. So computing the null space, dimension of null space, and column space. Yeah, question?
Just to clarify for the x equation, that one, shouldn't it be x plus 2z plus 9w?
Wait, hold on. Wait, the x equation?
Yeah, scroll up a little bit. It's 1 plus 2z plus 9w. I think you missed a sign.
Wait, so am I looking at this?
From your R matrix, it's 1, 0, 2, 9, not 1, 0, negative 2, 9.
Right?
Oh, okay.
The sign there.
Oh, okay. Yeah, gotcha.
Just wanted to clarify.
Yeah, okay. Yeah, so there should be I guess there's like a sign error or something. Okay,
Same
but
as the-
yeah, it's the same idea. It'll be in the solutions, they'll be written out correctly.